Welcome to the Siemens EDA podcast series on 3D IC heterogeneous integration brought to you by the Siemens Thought Leadership Team. I'm your host, John McMillan. If you are involved in any form of semiconductor and semiconductor packaging design, you will have seen and or heard the term 3D IC being broadly discussed and promoted. 3D IC is often referred to as a path to more than more, a reference to Gordon Moore's observation that the number of transistors on a semiconductor doubles every 2 years, and along with that, the associated speed, capacity, and throughput. Another tenet of this so-called Moore's law asserts that this growth is exponential. However, experts agree that semiconductors may be close to reaching their physical limits due to multiple technical and technology reasons, as well as business and or marketing reasons. This has led to design teams turning to the disaggregation of once monolithic implementation architectures into several smaller functional chips or chiplets, which are then reaggregated or integrated using a high-performance package. 3D IC refers to an integration methodology and technology. Today, in our first podcast in a 4-part series, we are discussing what 3D IC integration technology is and what exactly is driving it and why. I'm pleased to introduce my special guest, Anthony Mastroianni, who is the 3D IC Solutions Architect Director at Siemens Digital Industries Software. Welcome, Tony, and thank you for taking the time to talk with me today about 3D IC. And before we dive into the discussion, would you mind giving our listeners a brief description of your current role and background?
Sure, John. Thank you for the intro. I'd be happy to do that. Again, my name is Tony Mastroianni, and I've been in the semiconductor industry for over 30 years. I've been involved primarily in the design of custom integrated circuits, most of that time in the role of a design manager. I worked for a fabless semiconductor for the last 18 years, and in the last 3 or 4 years in that role, we started getting involved in working on 2.5D designs that were using HBM memories for some very complex system processors as well as 5G base station controllers. It became evident as we started doing those complex 2.5D designs that our packaging methodology did require some considerable overhauls and improvements. So I spent the last couple of years working in modifying our 2.5D design process. The company I was with was acquired last year in 2020. I started with Siemens, and they've asked me to drive their advanced packaging design strategy and methodology. So what I'm focusing on are complete solutions and workflows for 2.5 and 3D IC solutions, as opposed to just providing point solutions. So I'd like to talk a little bit about what's happening in the semiconductor and the design packaging space that's kind of driving this 3D IC. The reduction of the area of an IC transistor, as well as the increase in performance, which has been predicted in Moore's law over the past 40 years, has dramatically reduced over the last few technology nodes, coupled with a dramatic increase in cost and design complexity. The maximum size that an ASIC device can be manufactured is limited by the maximum reticle size, which is on the order of 25 millimeters per side. This limits the rate of increase in scalability of SoC devices in terms of complexity and performance. 3D IC technologies enable us to extend this scalability by deploying multiple chiplets within a single package. Furthermore, each chiplet can leverage different ASIC technology nodes for optimal power, performance, or cost. Another thing is HBM memories. These are high bandwidth memories. This is some technology that came out about 10 years ago where multiple memory chips are stacked on top of each other to give you a tremendous amount of memory in a very small footprint. And that's put into an unpackaged device, and that gets integrated into an ASIC on a 2.5D interposer. So that's where we come with the term 2.5D. And it started really with HBM memories. So that really kind of drove this methodology, and that's been around for about 10 years or so. So I talked about the device scaling. So by not being limited to how large a device you can be, we really can create much larger systems by putting multiple chips in a package. So the implications of monolithic design for certain products, such as high-performance compute and AI devices, will still continue to use monolithic technologies, but they could actually leverage from some of these disaggregation by, perhaps splitting the design up into a smaller set of chips. But in general, if you can fit everything you need in a single chip, you will get the lowest unit cost and the highest performance. But when you hit some of those limitations, that's where 2.5D or 3D technologies can allow us to extend the capabilities of those systems.
So there are a considerable number of growing pressures on traditional monolithic design. Can you tell us what approaches semiconductors teams have been adopting to achieving a device's functionality goals?
Sure. When we talk about putting multiple chiplets or chips into a package, there's several different underlying technologies. People have been designing multi-chip modules for many, many years, and that's essentially putting one or more ASIC chips into a single package and then connecting those with traditional packaging technologies. So that's referred to as an MCM module. And there's many different technologies, and that's a very mature technology, but there are some limitations of that. So when we get into 3D IC, this is really being driven by much more advanced packaging technology that allow you to integrate what I call chiplets. And a chiplet really is an ASIC that's been designed to be integrated with other chiplets within a package. And there really are two general classes, 2D and 3D. In 2D, we use the term 2.5D, and that really came from the fact that we're integrating a 3D HBM memory along with another ASIC. So it really is 2D integration. You're just integrating two chips on a single interposer. It may be organic or silicon, and then you're interconnecting those chiplets on that interposer using metal interconnect. The other class is 3D, and that kind of falls into two different categories. One of them is die stacking, and they're really kind of two general applications that are being deployed today. One of them is stacking memory on top of a chip. And one application that AMD and Intel and companies developing very large complex processor, they're actually decomposing those processors into smaller building blocks, and then they're actually taking some of the cache memories out of the die and putting those in a separate die and stacking that on top of the processor die. So that's what we call 3D. And in this case, it's really just taking some of the functionality, maybe memory, and putting that on top of the functional chip and then connecting those using the 3D packaging technology. Another application of die stacking would be in sensor type applications where you may have sensors that are gathering photosensors or whatever, and then that sensor chip would be stacked on top of, say, a memory chip. So you would take that sense data, store it in memory, and then maybe that would be stacked on top of a processing type chip. That's what we call die stacking. Now, 3D or true 3D is a term where you're actually taking an ASIC and you have the ability to actually split that ASIC into two chips and stack them on top of each other. So this requires the ASIC place and route tools to have the ability to not only place the logic in a traditional 2D manner on a chip, but now it can actually decide to partition some of the logic in one die that's stacked on top of another or below another. So this is really a very advanced methodology that will have some tremendous performance benefits, but it really is a newer technology. It is much more complex, so it's really not really in production today, whereas the other methodologies that I just mentioned are in production today.
So semiconductor design teams, they already have quite a range of choices to counter some of the monolithic challenges. But as you point out, none of them seem to be a one-size-fits-all or silver bullet, which I guess is why 3D IC integration is emerging. Please explain what 3D IC integration is and why it's technically different from the other technologies we just discussed.
So what we're talking about is putting multiple chips in a package, and primarily the difference between the traditional MCM is the packaging technology. So that may be either 2D or 3D. And the key difference there is the interconnect between those devices is really being implemented at the silicon level. So the geometries are considerably smaller. Since the wires essentially are much shorter and thinner, the resistance and the capacitance is considerably slower. So that gives you the benefits that you can implement significantly more connections between those chips. And also you have much less parasitics, which means you can run them at much higher speeds. So in effect, it is these packaging technologies, whether it be 3D or 2D, that offer the fine feature size of this interconnect enables increased performance. It allows you to do much more greater complexity, since you can do many more interconnects, and allows you to build systems with a much smaller footprint inside of a single package. So systems, in effect, can be decomposed into functions that are implemented as smaller chips, or what we call chiplets, as opposed to putting everything into a single homogeneous ASIC device. The other difference here is system designers now have more options to implement their complex devices and take advantage of some of the inherent benefits of 2.5 and 3D. So it offers them more options in developing their systems, taking advantage of some of the benefits offered by these technologies.
That makes it clear what 3D IC integration is and why it's technologically different. Can you tell us what a device design goals and or objectives would be that would make a 3D IC the right integration platform?
Any design goal or objective obviously is going to be unique to the particular design that the system designer is trying to design. So again, the benefits of 2.5 and 3D would need to be considered to see how those objectives and goals can be achieved. So the benefits that we're talking about through 3D IC integration are, again, since we have smaller wires, we have reduced latencies, which gives us, in the example of HBM memories, much higher memory bandwidth access. So you get performance advantages here, higher speed, better memory throughput. Scalability. So we do have some practical limitations on how large a device can be made. If we have the ability to split a chip up into smaller chiplets and integrate those on a larger interposer or stack them, we can scale our systems much more gracefully. Building an ASIC device takes a considerable time, cost, and time to market. It takes anywhere from 1 to 3 years to develop a complex SoC. But by having these pre-built building blocks, if you will, and maybe a smaller, less complex ASIC built into a system and package, it gives us the ability to implement different options of the product. So we can scale the product and have different product configurations leveraging this technology. Considerably shorter time to market, as well as reduced costs, because you're using packaging technology as opposed to the very expensive IC technology that we talked about before. The size, obviously, is smaller as well. So for the reasons we talked about, we can implement a smaller footprint that goes into whatever product ultimately this will be in, leveraging either the 2.5 or 3D technologies. And the power also, since we are connecting these chips that are placed right next to each other, the distances are much shorter. So we can run those at higher speeds at lower power, as opposed to putting chips on a board which may be several inches or a foot or more. So we do have lower power because we're driving these high-speed signals at much shorter distances. And also the benefits of cost. And the cost can become reduced by having smaller die, which would give us a higher yield and a lower unit cost for those chiplet components, as well as the NRE, because if we're integrating IP into an ASIC, for example, let's say a 56 gig SerDes, that may be on the order of $10 million for that piece of IP to be integrated into an ASIC. Now, if you need that functionality and that can be acquired from a chiplet, you're really just paying for the end results. You're not repaying for the IP costs for that. So there can be considerable savings in both the unit cost as well as the non-recurring engineering cost in deploying some of these technologies.
Those are very compelling points. So now that we understand what 3D IC integration is and why it's differentiated from other advanced integration packaging technologies, but sure, there must be some challenges in moving to 3D IC?
Of course, yeah, there's no such thing as a free lunch. So 3DIC does bring some challenges to the table, and we'll talk about some of these. First is really thermal. So in designing a traditional ASIC device, that device, will have a certain power profile, and then that power profile can be modeled, and then the package design really just needs to be able to deal with that simplified thermal power model. And historically, you could just analyze the package, make sure you have the ability to take that heat out of the chip and dissipate that, and you're done. But when you put multiple chips inside a package, that power profile becomes much more complex. So you do need to, rather than just having a very simplified single model, you have to deal with multiple chiplets in each of the power and thermal profiles of all those chiplets. The other thing that you need to be concerned with is the thermal interaction between these different devices. So one example might be, let's say, an HBM memory, which has an operating condition of 85C, may be sitting next to an ASIC that is designed to run at 125C. And if those devices are too close and you're not careful, the SoC can actually heat up that memory and knock it out of spec. So again, you have to analyze the thermal interaction between each of those components to make sure that you're meeting the thermal requirements of the device. Another thing which is unique to 2.5 and 3D type designs is mechanical stress analysis. So when you stack die or stack a large silicon interposer on top of an organic substrate, the thermal expansion coefficients between silicon and those organic materials are different, so they will bend and flex differently, and that can create some mechanical stress on the connections between those devices, which can cause failures and reliability issues. There are different design techniques that are used to deal with that, and really, since every design is unique, that analysis needs to be done with mechanical simulators to model that stress. One of the probably most complex issues that comes up in these technologies is the testability. So testing a single device, that technology is very mature, and generally it's a two-step process. So as the chips are manufactured, they get tested while they're still on the wafer. This is called wafer level testing. So there are probe cards that go and test the device, and if they're good, they'll go through, and then they're just marked if they're bad, so you don't package up the bad devices. And then once it's in the package, generally you're going to retest the package with the chip inside of it. That's called the final test. Now, when we get into 2.5 and 3D devices, we have multiple chips that are inside that package. So you do need to test the interfaces between each of those chips. You still need to retest those devices once they're in the package. So presumably, the chiplet providers, when they send those tests, have tested those before they ship those to their customers. So they are wafer tested before they're delivered to the system integrators. But during the assembly process, it's possible that they may have been damaged. So there is a need to retest those devices. So that would require the test patterns associated for those chiplets to be a deliverable provided from those chiplet vendors. The other issue is you don't have access to all the pins for each of those chiplets. So different test techniques and test tools and DFT tools are required to be able to test those 2.5 and 3D devices. Another issue is your power delivery network, designing and analyzing that network. So multiple chiplets may have different voltage supplies and different power requirements, different noise requirements. So that all needs to be considered during the package design process in making sure that you're delivering the power to each of those components and meeting the requirements of that. So there are other issues, but I'd say these are the primary things that need to be addressed in 2.5 and 3D designs.
Thanks, Tony. I think that helps us, it really does help us understand what 3D IC integration is and why it's differentiated from other advanced integration packaging technologies. So, what end target markets and applications are you seeing moving to or evaluating 3D-IC as an HI platform?
Really, this 2.5D market really started with the advent of high bandwidth memories. And as I mentioned, the applications well suited for those are high performance compute type processors that do have high memory bandwidth requirements and high capacity, and AI type applications. Those markets will continue adopting these technologies. But as an ecosystem of general purpose chiplets or building blocks becomes available to the general market, there really are no limitations in terms of what market these devices can be addressed. So I really can't think of any particular market that consumes ICs that would not benefit from some of these technologies. And this would benefit from some of the advantages that we talked about earlier, whether it be cost, NRE, performance, speed, and just footprint size. So I think it is really a true broad market that these technologies can leverage, the 2.5 and 3D IC packaging technologies.
Okay, thanks, Tony, for this highly informative and educational discussion for this first podcast on 3D-IC heterogeneous integration in our 3D-IC series, brought to us by the Thought Leader team, covering what is 3D-IC and what is driving semiconductor design teams to adopt it, and what advantages it brings. We're looking forward to the future podcast with you on the same topic, and thanks to our listeners for joining us today.